related machines.
Thanks, Afi. Thanks to the organizers for inviting me. So I'll talk about what's a fairly simple problem. So there are a bunch of jobs. Every job has a size, and I want to schedule these jobs on machines. Every machine has a certain speed. So for example, if I schedule the first job on the first machine, it takes 1.1 units of time to complete. If I schedule the second job, which is much longer, on the second machine, which is much faster, again, the running time of that job on the machine is the ratio of its size and the speed. So I want to schedule these jobs in a way that the total loads, so the load of a machine is simply the total time for which the machine runs. And I want to optimize some function of these loads. So once I have scheduled all the jobs, you get a certain load on every machine. I want to optimize some function of these loads. Now, in this talk, the problem we are looking at is an online problem, which means that when I'm scheduling a particular job, I don't see anything in the future. Okay, so I only see one job. I know what I've done till now. I need to schedule the job. And therefore, I would be looking at the competitive ratio of the algorithm, which is simply the ratio between whatever objective the algorithm produces to whatever is the optimal objective. And the optimal could be offline. It's just the absolute optimum. Okay, so that's the problem. So there's one thing I haven't specified yet, which is the function that I want to optimize. So what are natural functions? So again, I have this vector of loads after I've made all the assignments. This is a vector over the machines. What do I want to optimize? Maybe one simple thing one might want to optimize is just the total amount of processing I do, the total time for which machines run. This is just one norm of the load. This is very simple to do. I can assign all my jobs to the fastest machine. This will optimize this norm. Now the bad thing about this norm, of course, is that it doesn't do any kind of load balancing. Right? I have a lot of machines. I'm just using one of them. So one could go the other extreme, and one could try to optimize the make span, which is the infinity norm of the load, or I want to simply optimize the maximum load. And in general, one would probably want to optimize some balance between, one would want to achieve some balance between these two kinds of objectives, one that optimizes the total amount of processing, the other that optimizes the maximum processing on a single machine. So one can look at any arbitrary norm, any arbitrary what's usually called a LP or P norm. I'll call it a Q norm or a LQ norm, just so that I don't confuse with P's, which for me are processing times of jobs. Okay, so that's what I want to optimize. I want to optimize arbitrary Q norms for this problem. So this is what I want to do, Q norms and related machines. What's known? So this problem, of course, it's not known. That's why I'm standing here talking about it. But if you want to optimize the make span, then there are well-known algorithms to do it. In fact, the algorithm we will look at one such algorithm. These algorithms are usually called the slow fit or slowest fit algorithms. Okay, so we'll look at it soon. And of course, a lot more is known if I either generalize the problem or specialize it. So either I can generalize the problem to what's called unrelated machines, in which case the running time of a job on different machines are completely uncorrelated. In that case, the exact picture is known. All these competitive ratios that I have quoted are tight. And if I specialize it to identical machines, if all my machines have the same speed, again, the exact picture is known. Okay, so we know constant competitive algorithms in one case. We know in the other case that constant competitive ratios are not possible. Okay, so what's the situation for related machines? That's what I want to address today. Now, before I go there, I want to make one remark. So one thing you might guess from looking at this slide is that perhaps constant competitive make span algorithms imply constant competitive algorithms for all norms. But there is a qualitative difference between identical machines and related machines, or the kind of problem that I'm looking at. So in identical machines, you don't need to know what norm you are optimizing. You can make an assignment of jobs. You can come up with a schedule that's good for every norm. Okay, I can state the norm after the fact, and it would be good. It would be constant competitive for that norm. This is ruled out for related machines. This is not possible, which means that this algorithm that gives me a good make span bound is essentially useless for any other norm. And we are going to see, I mean, it's also this the fact that this algorithm does not extend is deeper, and we'll see technical reasons why it does not. But even at a superficial level, it is impossible that a single algorithm that does not know what the norm is can come up with a schedule that's good for all norms, unlike in the case of identical machines.
Okay. Clear even from 1 and infinity.
That's clear from even 1 and infinity. Yeah. All right. So the main result that I'm going to talk about is indeed there exists a constant comparative algorithm for scheduling jobs on related machines, and this will, as I just stated, this algorithm will be cognizant of the norm I'm trying to optimize. So it will take the norm into account. Okay, so if you are optimizing the L2 norm, it will use the fact that you are optimizing it. Okay, so let's step back and look at what this make-span minimizing algorithm is, the so-called slow fit algorithm. So there are various versions of this algorithm that get different constants. But here's a very simple version, and in fact I think this is the first version that was suggested. So just take your job and assign it to the slowest machine, where if after the assignment the load on the machine does not exceed twice opt. Okay? And assume for now that you know the value of opt. This is without loss of up to some constant factor. You can guess and double up your guesses. So you know the value of opt, you simply try assigning on all the machines the slowest one where you can without blowing up your load too much. That's the one you actually assign to. So of course if this algorithm succeeds, you get a true approximation if opt was known, if you had to guess opt, some constant approximation. So the proof essentially shows that for this algorithm you would be able to assign every job. Okay? You don't get stuck at some point. And I won't give you the proof, but it's a very simple proof. Now if we try to take this intuition that we have to assign to slowest machines subject to this kind of a criterion, how do we take this intuition and use it even for one norm, let's say, which indeed is an easy problem, but how do we use this intuition? Unfortunately, it's not so clear. How do I even define a slow fit algorithm for any other norm? Even if I tell you what the value of opt is, how do you define an algorithm like this? Because the value of opt, only in the case of make-span, it tells me what's going on in every machine. If I just give you a value of opt for any other norm, it tells me nothing about what's happening in individual machines. So you can try simple strategies. Maybe you take the value of opt, the overall contribution across the machines, split it up equally across the machines. And that gives you some bound on what's going on in each machine. But this is clearly bad. So for instance, if I have a lot of slow machines, and I'm only optimizing the one norm, I'll try assigning to all those slow machines, and at some point clearly I will have a huge value of the one norm. So there is no reasonable way that we can take a single value of opt and split it up across machines and hope to get a good estimate of what individual loads on machines are. So that's where the theme of this workshop comes up. I need a better lower bound on the value of opt. I need a more structural lower bound that tells me what's going on individual machines. And for that, what we're going to use here is a continuous relaxation of the problem. Okay, so we're going to solve a continuous relaxation that will tell me what's going on in individual machines. I'll use that in my algorithm. Okay, so that's the plan then. My algorithm has 2 stages. Of course, it's an online algorithm, so these stages are interleaved, but logically there are 2 stages. I'll first get a fractional assignment. Okay, and think of the fractional assignment as assigning tiny epsilon fractions of my job, and then I'll round that algorithm. I'll round the fractional assignment. Now one thing to note is that so maybe the most popular kind of algorithm that gets fractional assignments are these multiplicative weight algorithms. These are not very useful in this context. I want to get constant comparative algorithms. If you use any kind of reasonable multiplicative weights algorithm, it tends to lose logarithmic factors. Okay, so we are going to have to design a new fractional algorithm for this problem. All right, so let's start off with the fractional algorithm. At this point, I only want to get a fractional assignment. So the first thing is, how do I what is the objective that I'm trying to optimize in the fractional case? And I won't go into details of why this is the right relaxation, or this is why this is the right fractional objective. But let me describe it. So this objective has 2 terms. The first term is kind of what you would normally relax the integral objective to. So it just says that take the fractional load on every machine, raise it to to the power of q. Okay, and just from this point on in the talk, I'm only going to be talking about the q raised to q norm. So I'm not going to do this one raising the whole thing to 1 over q at the end. Right? This is something I'll do as a post-processing step. It doesn't really matter. It keeps things simple to look at this norm. So that's the first term. The first term is just the total fractional load on every machine raised to q. The second term is maybe a little more complicated, a little different, where I take the qth norm of every individual job, and then I split it up across the different machines. Okay, so this is a linear term. Second one is a linear term. The first one is clearly not linear. So I have these two terms. I want to optimize them, and we need these two terms. Just one of these terms has pretty bad interiority gaps, and that was known. This is not something new. Okay, so let me call them fx and gx. To understand the algorithm, let's do a couple of thought experiments. Yeah, and the thought experiments are simple ones. What if I only had one of these two terms? If I didn't have the other one, let's first start off with gx. If I only had a linear term that I wanted to optimize, what should I have done? Well, here the answer is very simple. I should always be assigning the job to the fastest machine. Right? This term is linear in the assignment. Clearly, the fastest machine gives me the smallest coefficient, so I should be assigning there. But let me rewrite that rule as saying that I want to assign to the machine that has the smallest gradient of gx with respect to x, the assignment variable. Okay? The same thing, I just wrote it in this manner because I want to generalize it later. The more complicated one is, what if I only had the first term? So one thing to note is that the first term, fx, is a load-dependent term. Okay? It depends on what I have done in the past. Second term does not care. It's a linear term, so it only depends on what I am doing with the current job that I have. So for the first term, if you think about it for a minute, you'll see that the best thing that I can hope to do is keep the derivative the same across all the machines. Because if my derivative becomes unequal in two machines, I can move a little bit of a job from the higher derivative to the lower one, and that will improve my overall objective. So the right strategy, if I only had the first term, is to somehow keep the derivatives equal. Okay? Which again, you can think of as assigning incrementally to the machine that gives me the smallest derivative on the first term. So both these terms, individually, if I were trying to optimize, I should really be assigning that infinitesimal job to the machine that gives me the smallest derivative. And indeed, that's what we do in the actual algorithm. So of course, the natural extension of these experiments would be to say that I take the derivative of the sum and assign it to the one that minimizes this. This by itself is a little cumbersome and it's hard to work with, but it's in the same spirit. We assign to the one that minimizes the maximum of these two derivatives. Okay, so it's the same. Think of the sum if that's more convenient. It's easier for the proof if we use the max. Okay, so that's the entire description of the fractional algorithm. Very simple algorithm. How do we analyze this algorithm?
So
yeah.
You just when the job comes, you sort of slowly split up the job and
yeah, just split it up into tiny fractions, or you can think of it as a continuous algorithm. Okay, so that's the algorithm. So let's try to analyze it. So before we analyze it, it will be useful to understand the structure of what's going on. So some structural property. Yeah. So let us try to map these derivatives of these two terms, f and g, against the speed of the machines. So I am drawing the machines in decreasing speed. So how do the derivatives of the second term, the linear term, look in terms of the machine in terms of machine speeds? So clearly that's a linear term. The derivative just keeps increasing as my machine speed decreases. Okay, so this one is pretty straightforward. The key observation is that if I looked at the first term is more tricky, it's load dependent. But if I looked at the first term, I claim that my derivatives actually go exactly the opposite way. So throughout the algorithm, my derivatives will keep decreasing with decreasing speed. Okay. So let me give some intuition. I won't give a formal proof of this, but let me give some intuition for why this is true. So what was I doing? I was taking the max of two derivatives and I was optimizing for that max. If the derivative of fx was always the max, if it was always bigger than g, then I would keep all the fx's, the derivatives, equal. Right? That's what we just argued a couple of slides back, that I should be keeping all of them equal. If fx was always winning the max, then I would basically not get to see g at all in my algorithm. But fx does not win the max comparison all the time. Sometimes for slower machines, g might win the max comparison. What does that do? That forces me to assign my job to faster machines, even though that have a higher value of the derivative. But if g wins the comparison, then I always go to a faster machine. So what that means is that it skews the derivatives on the first term in exactly the opposite way of the second term. Okay, so I have this picture, and the algorithm always maintains this monotonicity property. Why is this useful? Well, let's look at two cases. So of course, where is the algorithm actually assigning? It goes to the middle. There are two curves. It goes to the middle and assigns right there. So if it was continuous, it would assign exactly where the point where these two curves cross. It's discrete, so it assigns at one of the two neighboring jobs, two neighboring machines. Okay, so how do we use this? So let's look at two cases. The first one is the easier one, where opt actually assigns to a slower machine. Here the comparison is obvious. I am assigning at lower derivatives than opt is. Opt's derivative on the second term itself is higher. So clearly I can charge whatever increase I am getting in my objective to whatever opt is getting. Okay? So remember, g is load independent. The second term is load independent. It doesn't matter what opt's current state is. It just depends on what opt is doing with that job. The trickier case is if opt went to a faster machine. So here it is true that in the algorithm on that faster machine, I have a larger derivative on f. But that's in the algorithm. Maybe opt was clever and had a very small derivative on the value of f on that machine. Okay, so how do we get around this? So here I will cheat a little bit. Take my word for it that this cheating is permitted. So let me assume this cheating is that that this curve on the derivatives on the first term is true even if I only consider jobs of this kind, jobs where opt is going to a faster machine. This is not true in general, but losing some constant factors, we can make this work. Okay? So imagine that I had this stronger property, that just for these jobs, I have this slope of derivatives on the first term. Then I claim life is good for me. Why? So this is how the algorithm looks. How does opt look? Its derivatives can be completely uncorrelated. It can be completely arbitrary. However, I have a prefix property here. All these jobs, opt went to faster machines than I did. So if I cut this slope off anywhere, then opt has more jobs to the left than I do. So using this fact, I can smooth out opt's irregular curve into something that looks like this without increasing opt's objective. So I can smooth it out to something where opt has a curve on derivatives that dominates my curve point-wise, and the objective of opt in this smoothing has not increased. So that says now I am fine because I can now just charge my costs to opt's cost on the same machine. Okay, so this was a bit hand-wavy, but this is the basic idea how the proof for the fractional algorithm works. Okay, so eventually this gives us a constant competitive ratio for the fractional problem. But this is just a fractional solution. If there are any questions I can answer about this before I go to rounding. Okay, so let's go to rounding now. So I have this fractional solution. How do I round it? So yeah.
Is this somehow related to what Mario spoke about? Can one make any connection?
Maybe I don't know an explicit connection.
In some sense, it's sort of like your objective is a convex separable function, and some resource allocation, right? So, but the fractional problem, she is solving a fractional problem. Is there anything possible? I mean, I don't know if it satisfies the curvature conditions and stuff.
Yeah, I mean, you have to go and check the, yeah. Yeah, I don't.
So does it depend on Q, the competitive ratio?
I mean, it's a constant, like absolute constant. Okay, so how do we round this? So let's say I come up with some fractional assignment of the job. So one very natural thing to try maybe is to take the median of, so this fractional assignment gives me a distribution of the job across the machines. One maybe natural thing to try is to assign the job to the median of this distribution. Why is this good? So let's look at again these two terms, fx and gx that I have. I claim that if I always assign to the median, then I'm always good at least on the second term in this objective. Why? Because half my job has been assigned to slower machines by my fractional assignment. And the slower machines have a larger value for gx, irrespective of what's happened with the other jobs in my system. So as far as gx is concerned, I'm always good if I assign to the median. Problem is with fx. In general, I should also be good in terms of fx because half my jobs went to faster machines. And I have some intuition which says that on faster machines, the derivative of fx was even higher. Right? So somehow I should be able to charge my cost to the faster machines. But just this clearly is not a good solution. For example, think of a situation where the fractional algorithm simply splits every job equally across a bunch of machines. Then this median rounding will send all the jobs into one machine in the middle. Right? So that's clearly not a good algorithm.
So yeah. Your rounding is tailored to your first part. It's not going to do it for an arbitrary.
It will do it for an arbitrary assignment, fractional assignment. So the intuition for now is tailored to the first part, but eventually it will do it for any arbitrary assignment. Okay, so how do we make this work? Suppose I really like this idea of assigning to the median machine, which seems to have some nice properties. So
what is, I mean, this offline algorithm has a constant approximation.
No, this is online.
In the offline world, how do you round if I have a fraction solution? I mean, there too they solve this convex program and then they round, right?
Yeah, so in the offline world, I think the algorithms that I'm aware of don't go through relax and round, but maybe there is some rounding. I'm not 100% sure. Okay, so if I want to stick to this plan of assigning to the median, here's one idea. So maybe instead of thinking of these as individual machines, let me think of each machine as a set of machines. So as I go down this list, these are slower and slower machines. But if I could if I could make sure that the total speed of the group of machines at any of these layers is at least the sum of speeds of all the faster machines, then I would be in much better shape. Because half my machines were being sent to faster machines. And if I go to the median group overall has processing power or sum of speeds that captures all these faster machines. Okay? So if I think of these as machine groups instead of individual machines, and somehow manage an exponential increase in every step of the total speed, then maybe some rounding algorithm like this could work. Okay? And that's what we try to do. So here's what I want to do. I want to somehow get machine groups such that as I go down to slower machines, the total speed of the machines, the sum of speeds, keeps doubling. So I have slower machines, but I have many more of them. So that if half the jobs were being assigned to faster machines, just assigning them to the median group is enough. The median group has enough processing power that covers all the faster machines. But in general, an instance may not have this property. Maybe all my processing power is concentrated on high-speed machines in the instance. So we use a general technique which takes an arbitrary instance and converts it into an instance that has this property. And we do this greedily. So the first machine becomes a group on its own. Then we keep going until we collect a total speed that's double the first group, okay, and replace those machines with machines that are half the speed of my first group. And keep going. So again, I get a bunch of machines. The total speed of these machines should double my previous group. So it's exponentially increasing in the total speed. But then I replace them by machines that are uniform. And we show that this is a technique that has nothing to do with the particular problem at hand. You can take any scheduling problem with related machines and convert it make this transformation of the instance. And we show that this transformation only loses a constant for any norm. So no matter which norm I'm trying to optimize, of course, the transformation itself uses the norm. So you have to be careful in how do you do the transformation. It must use the value of the norm, but it only loses a constant. So any schedule on the original instance can be mapped to the translated instance and vice versa. So now I have an instance that looks like this. It's a very nice instance. My machine speeds keep doubling. Machine speeds keep halving, and my total speed, the sum of machine speeds, keeps doubling. So now I rerun my fractional algorithm, but now on these machine groups, thinking of these entire groups as single machines. So the fractional algorithm only decides which group to send it to. Then I use my median rounding. That gives me an integral assignment into a group. But the good thing is that a group now has machines that look exactly the same. So I can use a post-processing on this, which just is an identical machines algorithm inside the group. Yeah, and that's the overall algorithm and gives me a constant. So just before I end, this is the last slide. These techniques also solve more general problems. So for example, if instead of one-dimensional, single-dimensional loads, I have multi-dimensional loads. You have many different, let's say, resources, and the job needs multiple resources. It also solves the multi-dimensional or vector scheduling problem. And that's all I have. Thank you.
Questions?
So your rounding solves Chandra's question, right? The decoupling.
So the fx plus px you had, so the optimization problem was to maximize that subject to just a constraint that says sum of xij's should be 1 and they're positive. Minimize that? Minimize that subject to that.
That's what this is solving.
So there was no other uncoupling constraint.
So the only issue is that like in my description, I used an integral optimum, but this can be changed to the fractional optimum if you want.
Like if you had just taken the sum of gradients, had you just run greedy, that would give you.
So my suspicion is that might also be a good algorithm, but the analysis becomes messy. The analysis is much simpler because we lose these properties, this structural property, and then the analysis gets a bit messy.
Just like 1/2.
No, but I mean I lose this structural property. This property is something that's crucial for my analysis, and I lose.
Analysis, but like a simple analysis should give you, because you're just maximizing monotone function, and then that just should give you the fractional thing. The simple greedy should give you like 0.5 competitive ratio.
0.5 on what?
1/2 competitive ratio. Just
Yeah, that's not obvious to me.
Result is minimizing a monotone function.
Oh, you're minimizing a.
Yeah.
Oh, my bad. Yeah.
More questions? Let's thank all the speakers of the day.